Thanks, Robert. So originally, when I sent in my topics, I thought I was going to talk about adiabatic quantum computing as well. And then Mohammed sent me the sketch of his talk, and I realized I wouldn't have very much to say on adiabatic quantum computing. And indeed, not much is left. However, I decided that last minute, probably not a wise decision, I decided that I would say something about adiabatic quantum computing after all. One topic that Mohammed didn't touch is a different approach to adiabatic quantum computing, which is based on differential geometry. So the basic idea is that we can think of an adiabatic quantum computation as trying to perform some kind of an optimization of a path. And the path is the path that takes us from the initial to the final Hamiltonian. So to make that concrete, here's the initial Hamiltonian, and there's the final Hamiltonian. And we're trying to find the optimal path between the two on some curved manifold. So why are we getting a curved manifold? Why is this a problem in differential geometry? So the way to understand that is to imagine that you have control knobs. So here these x's, x1 through xn, are some control knobs that you as an experimenter can compute. For example, they could be electric fields, magnetic fields, things like that. And together they belong to some manifold, a curved manifold n. And as you vary them as a function of time, tau, you trace out a path. And the Hamiltonian is dependent on these control knobs. So here's our Hamiltonian, and it depends on this path, this vector x, which depends on time. And the vector x is some trajectory along this curved manifold. And in adiabatic quantum computing, we have a boundary condition. We start from a given initial Hamiltonian, end up with a given final Hamiltonian, the one whose ground state represents the answer we wish to find. And so here are some examples of such paths or interpolations. This is the simplest one, a one-dimensional interpolation where we start. And by the way, I'm working in units where tau is normalized time, so tau is actually the real time divided by the total time. Okay, so when tau is 0, we start in the Hamiltonian H0, the initial one. Then when tau is 1, when t is the final time, we've ended up at the final Hamiltonian H1. So this is a linear interpolation, but we could imagine much more general interpolations. For example, here's one that depends upon two parameters. So this would be a trajectory on a two-dimensional manifold, which depends on parameters x1 and x2. And in general, you can imagine a trajectory that moves on an m-dimensional manifold, as I started out with. Okay, so the question is, now that we have identified the manifold, what's the manifold? It's the manifold of the control parameter. And typically, these are continuous. So, and if they're not, then, well, let's make them continuous. So we have a setting for differential geometry. Then the question is, what is the differential geometry of this control manifold? In other words, can we identify some kind of an adiabatic metric tensor which describes this manifold? And then can we deduce from it a Riemannian geometry? And the answer is yes. It turns out that this can be done in at least two ways. At least I know of two ways. One is to set the problem up as one where we try to minimize the total time. Minimize the time it takes us to get from the beginning to the end. Of course, that's a very sensible thing to do. In adiabatic quantum computing, we are trying to get to the final answer in the least amount of time possible. And then it turns out that you can derive a metric tensor, and I wrote it down here, and I'm not going to try to explain too much, except to say that what features in this metric tensor is the minimum gap, delta is the gap, and derivatives of the Hamiltonian as a function of its control parameters. So if you want to read more about it, look at this reference. An alternative to minimizing the total time is to minimize the error. Minimizing the error means to minimize the deviation between the actual states, the solution to the Schrödinger equation, and the desired ground state. Okay, so this is an alternative to minimizing time. Let's try to minimize the error. And if you do that, you actually arrive at a slightly different metric tensor. And it turns out that this approach is also tightly connected to the phenomenon of quantum phase transitions, which shouldn't be too surprising after we heard Mohammed's talk. connection between adiabatic quantum computing and quantum phase transitions. Turns out that a metric that was proposed to describe quantum phase transitions is strongly related to a metric that we obtained via this approach. Okay, so what happens when we go through all this? I just want to flash a result that we can obtain using this optimal differential geometry approach. So let's go back to Grover's search. So here's kind of a generalization of Grover's search. In a two-dimensional setting, there are two parameters, x1 and x2, and we're interpolating between a projector, PA perp and PB perp. PA is simply the projection, or 1 minus the projection on the equal superposition state. And PB is 1 minus the projection on whatever the marked item is, the one that we're trying to find. Okay, so this is another way to write the Grover problem, but in terms of a two-dimensional parameter problem. And now we can try to optimize the path in terms of these two parameters. So let's try to find an optimal trajectory on a two-dimensional manifold, which solves the Grover problem. So the easy case is actually to start from the one-dimensional case. In the one-dimensional case, I just make x1 1 minus x2. Okay, so this is actually just a single parameter that we're trying to optimize. And it turns out that if you solve the variational problem, if you solve the Euler-Lagrange equations, which are obtained from this differential geometric setting, you recover precisely the path which was obtained by Roland and Cerf in a paper that Mohammed mentioned, where they showed that in order to solve the Grover problem correctly, you have to move fast and then slow down, move fast and slow down near the gap and then move fast again. This is precisely the interpolation or path that they found in the one-dimensional case. The time it takes you is order of square root n. That's just a feature of the Grover problem. What happens if you go to a genuine two-dimensional setting? In that case, we can't solve it analytically, but we can solve the problem numerically. So here's what we find. First of all, as far as the path is concerned, just to show you that there's a difference, this is kind of a weird plot, but what it shows is the two parameters, the interpolation parameters x1 and x2. So starting from zero there. So this way we move forward in time. And what is plotted here is actually the curvature of this manifold, the two-dimensional manifold. And this curvature is, it's one component of the curvature tensor, and it sort of blows up over here at short times, and I don't want to get into the reasons exactly. But the only thing I want to point out in this plot is that RC stands for Roland Cerf. That's the one-dimensional path. So you see that along this curve here, the RC curve, x1 is 1 minus x2. Okay, so this is the one-dimensional path. And the two-dimensional path, QAB, quantum adiabatic brachistochrone, is the one we find by numerically solving the optimization problem. You see that it actually diverges a little bit from the one-dimensional path. And it diverges in an interesting way. It follows a path that has less curvature. Right, over here, you can clearly see how it has less curvature than the optimal one-dimensional path. Okay, so the two-dimensional path is slightly different. It uses a little bit less curvature. And what do we gain from doing this? Well, let's define the error between the actual final state, the solution to the Schrödinger equation, and the ground state, the one that we wish to find, the marked item. So this is the error, 1 minus the overlap squared between those two. And let's plot here as a function of time, as a function of the total time, let's plot the difference in error between the one-dimensional path and the two-dimensional path. Okay, so what this means, and this is on a log base 10 scale. So what this plot means is as you increase the total time, you get these oscillations. And blue means that the two-dimensional path has a smaller error. Red means that the one-dimensional path has a smaller error. Okay, so in other words, whenever you see a blue dot, the two-dimensional path wins. For the same amount of time, it produces a smaller error. Whenever you see a red dot, the one-dimensional path wins, it has a smaller error. As you can see visually, the two-dimensional path wins most of the time. Okay, so in this problem of Grover search, we're able not to speed up by finding optimal path, but we're able to, for most times, we're able to reduce the error relative to doing a one-dimensional interpolation. Okay, So that's all I want to say about this. If you're interested in the details, go ahead and read the papers that I listed up there. And now I want to switch gears, unless there are any questions about this. Happy to take questions at this point. Okay, so if there are no questions, I want to switch gears to the main topic I would like to discuss this afternoon. And this is the subject of various methods for reducing and preventing and also correcting errors in quantum computation. So this is unrelated to adiabatic quantum computing, although some of the methodology and some of the formalism will be reminiscent of what you heard from Mohammed earlier this morning, in the sense that the analysis that I will present for reducing errors and basically the circuit model of quantum computation is mostly Hamiltonian based, although not exclusively. We will also make use of the formula that you heard about earlier in the week, for example, from Daniel Godson. Okay, so can I get this to move? Here we go. All right. Oops. Going a little too fast. There we go. Okay, so this is the outline for the main talk. I'll talk about symmetry and how it's related to preserving quantum information. I'll talk about system math, decoherence, and then I'll talk about how we can understand a whole bunch of buzzwords here in terms of the unified perspective that comes from this symmetry point of view. And then I'll talk about decoherence in subspaces and noiseless subsystems, both at the level of theory, examples, theoretical examples, and also experimental examples. And then in the second half, after the break, I'll switch gears and I'll talk about dynamic decoupling, which is a different method for overcoming decoherence. Okay, please take this seriously. No, seriously. I mean, this is a tutorial, so do interrupt and do ask. Okay, so as we all learned in high school, in some cases, and a little later in life, symmetry is related to conservation laws. Okay, so as you know, when you have translational symmetry, then momentum is conserved. When you have rotational symmetry, angular momentum is conserved. So why not associate symmetry with the attempt to conserve quantum information? Okay, so that is the idea of decoherence in subspaces and noiseless subsystems. They're a method to preserve information by hiding it, so to speak, from the environment. So here's a big Hilbert space of the system, and here there's a little quiet corner. And that little quiet corner is a decoherence in subspace, where we're going to store some protected degrees of freedom, which are going to represent quantum information for us. So that's part one of the talk. And part two, as I mentioned, will be about dynamic decoupling, which is kind of a different strategy on the face of it, although intimately related to the same idea of hiding information. But more about that later. Okay, so I'd like to start by reviewing once more where the errors come from. Mohammed talked about this a little bit, but let's go back and understand in a more systematic way where decoherence arises. Okay, so you've seen this, Hamiltonian for the universe, and it comprises a system Hamiltonian, a Bath Hamiltonian, and a system Bath Hamiltonian. Bath environment, same thing. I'll use Bath from now on. And the system Bath Hamiltonian, we can always decompose it in terms of a sum of system operators tensored with Bath operators. Okay, now what is the standard procedure for arriving at the dynamics of the system alone? The system is our quantum computer, obviously. The standard trick is to propagate the density matrix of the joined system Bath, starting from time 0, via this joined Hamiltonian H, and then trace out the Bath. Okay, and if you do that, you arrive at the so-called Krauss operator sum representation, this expression here. where typically these coefficients C sub k are positive. Okay, but not always. And this is an important comment I want to make right now. In most textbooks, you will find this expression, and you will find that these coefficients C are positive numbers. But it doesn't always have to be the case. In fact, the C's are positive numbers if and only if the initial system bath state is one that is purely classically correlated. Or more precisely, one that has zero quantum discord. Okay, this is a recent result. Normally, people just plug in a tensor product state between the system and the bath here at time 0, so a totally uncorrelated state. But that's not a general thing that can happen. System and bath could start even in an entangled state at time 0, or certainly in some kind of other correlated state at time 0. And if that's the case, if the initial system bath state is one that has some quantum correlations in it, it could even be separable. It has some quantum correlations in it, then you will find that these coefficients here can be negative. So the most general map you can get from the initial system state to the final system state is what's called a Hermitian map. When the coefficients C are positive, you get what's called a completely positive map. Okay, and those are the workhorses of quantum information. Those are the ones you will always find in quantum information textbooks. But the more general scenario is where you get a Hermitian map with possibly negative coefficients. And that is the most general type of map that we can get from this recipe, this general recipe of quantum dynamics. Okay, now, from now on, I will in fact assume that these coefficients are positive, which means that this state is, the initial system bath state is purely classically correlated. And then from now on, I will only have to deal with completely positive maps. Okay, so what is decoherence? Mohammed gave one definition, which involved, well, it was a definition for a qubit, and it involved the decay of off-diagonal elements, although he was careful to point out that if you change basis, then the shape of the density matrix can change. I would like to define decoherence simply as anything that's non-unitary evolution of the system. Okay, and that's going to happen whenever these operators, these Krauss operators here, when there's more than one of them, and in that case, we get non-unitary evolution. Okay, so that's decoherence in general. Now we can start to make approximations, and if we make the so-called Markov approximation, where we assume that the bath has a very short memory time, or a very short correlation time, then we can arrive at the Markovian master equation, the Lindblad equation, which I also mentioned extensively in their numerical simulations of their qubits. And it has this form, and the operators that appear in the Lindblad equation are these system operators that appear in the system bath on its own. Okay, so that's the general origin of decoherence. And now, in order to understand how we can overcome decoherence using symmetry, I want to go back to a very simple classical problem. The idea is to try to use symmetry. Okay, so what if, it should have been, what if there is a symmetry? What if there is a symmetry? Let's consider the following simple game. We have 2 coins. I've written down all 4 possible states of 2 coins. And now let's assume that we have an environment which has some kind of symmetry. And the symmetry is that the environment can only flip the 2 coins together. So if it flips the coins, it flips both of them together. It can do so at random times. That's totally out of our control. But it will always flip them together. So if that happens, okay, I don't know if you can see that, but kind of fast, but, oops. Okay, so heads flips the tails, and tails flips the heads. All right. So now the question is, how do you reliably store a single bit, classical bit of information in this system? Any ideas?
Parity?
Parity. I heard parity. Okay, good. So indeed, parity is the answer. Of course, what we should do is define the state heads-to-heads along with the state tails as a single, let's say, logical zero. And so that's the even parity subspace. The odd parity subspace is going to be a logical 1. Now, because the environment can only flip both bits at the same time, if it goes from heads to tails, we don't care. We still call that 0. Okay? So this is a noiseless subspace, a classical noiseless subspace. We've exploited symmetry in order to store information in a robust manner. No matter how fast the environment does the flipping. Okay, so in other words, no matter how strong the interaction is. Remember, in Mohammed's talk, it was important that the system bath coupling was weak. Here, I do not care about strength. The interaction can be as strong as you wish in the sense that this flipping can happen at whatever rate, but it has to have a symmetry. As long as it has a symmetry, the strength is irrelevant. Using the symmetry, we can perfectly store a classical bit in this case. Okay, so if you understand this, you can pretty much go to sleep. The rest is quantum details. But maybe some of it will be interesting. All right. So now, keep in mind this idea of symmetry. I want to digress and present a unified mathematical view of all these different error correction and error prevention methods. All these referring to error correction is probably what Daniel Gosling talked about, and error prevention is what I'm going to talk about. So let's start again with the error model. Here it is, completely positive maps. Okay, I got rid of my coefficient Ck. I can absorb them when they're positive. I can just absorb them in the cross operators. And let me now define what a decoherence-free subspace is. So, decoherence-free subspace, quantum decoherence-free subspace, unlike the classical one we just saw, is the following beast. We take the system Hilbert space and we split it up into a direct sum of two subspaces, A and B. A decoherence-free subspace is a code. A code is a subspace itself. Okay? So code C, it's all those states, all density matrices, on A, such that the noise, the action of the noise map is trivial, preserves states. That's a decoherence-free subspace. Okay? It's a very simple idea. Pick a subspace and ensure that the action of the noise map is trivial on that subspace. Okay? What is a noiseless subsystem? It's a slightly more complicated idea. Instead of just splitting the Hilbert space into a tensor sum, let's assume that the first subspace, A, has additional structure. It is itself a tensor product. The noiseless part and what's called the gauge part. Okay. And now a noiseless subsystem is kind of a generalized decoherence subspace. What we ask is that states are not just preserved if they are in a piece of them is preserved in the following sense. Okay? Take them at the noise map, apply it to states in A, and then trace out the gauge qubit, or the gauge, not qubit, excuse me, the gauge subsystem. And if after this operation you got back just the piece that lives in N, then you have a noiseless subsystem. Okay, so in other words, to simplify, we don't care about what happens to the gauge factor. We only care about what happens to the N factor. That's a noiseless subsystem. This is a passive method of protecting quantum information. We haven't done anything. We're just setting demands. Who are we to set demands? Well, we'll see if the environment is willing to cooperate. Okay, we'll make it happen. What is a quantum error correcting code? Well, it's actually just like a decoherence-free subspace with one extra piece. Again, we have a decomposition of the Hilbert space into A plus B. An error correcting code is all those states such that, in addition to what we said about the decoherence-free subspace, there is some completely positive map, R, the recovery map, for which, if we apply it to the noisy state, we get the state back. Okay, that's an error correcting code. Well, the only difference is that we're adding this active component of recovery to the DFS definition. What is an operator quantum aircraft control? This is the most general form of quantum aircraft known to date. It is actually a cousin of noiseless subsystems. It's, you see, the same story. Now we have the gauge part. And now we also have the additional demand that we have to be able to apply a recovery map to the noise before we trace out the gauge part. And then get back the state. Okay, so this is an operator quantum aircraft control. So you see this hierarchy, there's a clear logical development there, addition of structure. This is passive, we don't do anything. This is active because we're doing recovery. Now, from this perspective, we can think of a DFS as a quantum aircraft control, or a quantum aircraft control as a DFS. Here again are the definitions of the two. And if you compare the definitions, you see that a DFS is just an aircraft encode that has a trivial recovery operation. Right? If R is identity, then we get the DFS definition. An aircraft encode is a DFS provided we take recovery applied to the noise together as the entire operation. Okay, so this is a unified view of decoherence subspaces and aircraft encode. Similarly, we can unify the subsystems and operator quantum aircraft encodes. It's the same story. You know, the subsystem is an OQEC with a trivial recovery operation, or an OQEC is a noise subsystem with respect to the map that is noise followed by recovery. Okay, so this is the unified view of these various different methods. And it's kind of a powerful idea because it allows you to use results from one in another. Okay, but this is in fact not the most general thing we can do, because so far all I've asked is to preserve my systems. Right? We're just preserving states. But of course you want to do more in quantum computation. In quantum computation you want to compute. So the next thing we'd like to do is to be able to talk about decoherence subspaces and the other members of this hierarchy, which are able to support unitary operations. So this is what is called a unitarily invariant DFS. Unitarily for the unitarily invariant noiseless subsystem. I'm only going to talk about the DFS to keep it simple. So what's a unitarily invariant DFS? It's a subspace in which the evolution is purely unity. So far the evolution was just identity in a DFS. Now I want it to be unitary in order for us to be able to apply some kind of interesting computation. Okay, so here is a more precise idea. Let's say that we can decompose the system Hilbert space into a direct sum like before, and I'm going to call it HD plus HD per. And now let's partition the system density matrix into blocks according to the same structure. Okay, so rho D is where I'm going to store my information, and I'm allowing 3 other blocks. The blocks correspond to this tensor sum. And let's assume that where we're going to store the information, it's not empty. Okay, so rho D is not 0 at time 0. And note something important in this decomposition. I'm allowing what I call imperfect initialization, which means that I'm allowing these 3 other pieces here to be non-zero. And that's going to be okay. Right, so even though the other parts of the Hilbert space are going to be occupied, even coherences between our decoherence subspace and the orthogonal component, even coherences will be allowed. It's still going to be okay. And we will be able to perfectly evolve unitarily information in the DFS. Okay, so what is now a DFS, or a unitarily invariant DFS? HD, the piece where we're storing the information, is decoherence free if and only if the initial and final DFS block, that's this, are unitarily related. Okay, so we want rho D at time 0 to evolve unitarily into rho D at time 0. And UD is a unitary matrix. Okay, so this is just a definition. What are the conditions for this to happen? Can this ever be realized? And the answer is yes. So in the setting of completely positive maps, I'll give 2 characterizations of this. One, CP maps, the other one, Lindblad master equations. So in the setting of CP maps, here is the CP map again. The theorem says that you can get a unitarily invariant DFS, one where information is stored and involved unitarily, provided that the Krauss operators have this particular form. Okay, they have to have a unitary, an identical unitary piece in the upper left-hand corner where we store information. Zeros on the off-diagonal. The zeros ensure that there is no leakage into or out of the DFS, and some arbitrary operator down here on the right-hand corner. Okay, and if all the Krauss operators have this form, that means that they act in a unitary way on the DFS. Okay, so this is a formal characterization of what a unitarily invariant DFS is. And again, the question is whether this can ever be realized in real life. And of course, the answer is yes. But before we go there, what about the Markovian case? In the Markovian case, the conditions are slightly different. Here's the system Hamiltonian acting on the state, and here are the Lindblad operators, response decoherence. Now we have to treat those two pieces separately. So we are going to get a unitarily invariant DFS provided the Lindblad operators have this kind of structure, just like the Krauss operators on the previous slide, with an identity matrix here. But also, we have to make sure that the system Hamiltonian doesn't cause transitions outside of the DFS. Okay, so we need these zeros on the off-diagonal, so that the Hamiltonian itself is not going to be the culprit and cause leakage out of the DFS or into the DFS. We have to keep these two things separately in check. Okay, so what does this mean? It means that the Lindblad operators act as identity on the DFS, and the system Hamiltonian preserves it. That's the condition for unitarily invariant DFS, and you can come up with conditions for the other three types of information preserving structures. Indeed, I challenge you to prove the sufficiency and necessity of these conditions that I just presented. Okay, the sufficiency is easy. You just plug it in basically and see that it works out. The necessity is kind of hard, but it's doable. And then it would also be a very nice exercise to try to generalize these two theorems that I just presented to Noiseless subsystems, back-correcting codes, and operators correcting codes. And don't look in the literature because it's been done. Keeping it relevant. Okay. All right. So what about symmetry? And how do we even find and make these DFSs? Okay, so to see that, it is actually very instructive to go back all the way to the Hamiltonian formulation of the problem. So once again, here is the standard Hamiltonian formulation. We have the system plus the system BAF plus the BAF Hamiltonian. And now what is that we want? What is a DFS? We want to find a subspace where the system BAF Hamiltonian acts trivial. That's really all we're after. Right? If the system BAF Hamiltonian has no way of coupling the system and the BAF, then they will evolve separately. So in other words, we want to make the system BAF Hamiltonian act as identity on the system, and it can do whatever it wants to the BAF. We don't care. As long as the system BAF Hamiltonian doesn't entangle system and BAF, then we're going to be fine. The other thing we have to keep in mind, as you recall from the Lindblad case, is that we have to make sure that that system Hamiltonian itself doesn't mess us up. It shouldn't cause transitions into or out of the DFS. Okay, so with this in mind, here's a theorem that's slightly more useful than the previous ones. This is now constructive. This tells us, given the system BAF Hamiltonian, what it is that we need to do in order to identify the DFS. And it says the following. Consider the algebra generated by the system operators. So by the algebra generated, what I mean is just take these S's, take their Hermitian conjugates, throw in an identity, right, mix it all up, create polynomials in these operators. That's the algebra. So consider this algebra, and let's assume that the system Hamiltonian is such that it commutes with this algebra. Okay, this is, as long as we can engineer our system, we should be able to take a system Hamiltonian which satisfies this demand. And this demand, of course, has to do with HS must preserve the DFS. All right, so now, the theorem says that there is going to be a DFS. More precisely, the dimension of the DFS equals the degeneracy of the one-dimensional irreducible representations of this object. Okay, so I know that's a mouthful, and I'm going to explain it. But already here you should get the message connecting symmetry to the problem, because as every physicist knows, degeneracy arises from symmetry. Okay. So the fact that we're talking about degeneracy means that we are really looking for symmetry. Symmetry is in the way that system and bath couple. Okay, so here's an example, just to illustrate what's going on. The simplest example, the simplest non-trivial example, called collective dephasing. So let's say that we have two qubits, and they're in some states, slide 1 and slide 2. And let's say that there's, well, let's imagine these are spins, and let's say there's a magnetic field which has a long wavelength. Remember the example of the two coins flipping? Why was the environment in the case of the two coins unable to independently flip the two coins? It could only do them together. It's because it has a long wavelength in some sense. Okay, so this is the same situation. We have a long wavelength environment. And all it does is it is going to couple along the z direction. And in Canada, I guess I should say z. So the result of this is that the state of each qubit, qubit j, is going to acquire a phase, a relative phase, and its phase theta is a random number, but the important point is that it doesn't depend on the index j. In other words, it doesn't depend on whether the qubit is qubit number 1 or qubit number 2. Okay, so that is the collectiveness, the symmetry that I'm assuming. So let's say that's the model. In terms of the Hamiltonian, what I'm saying is that my Hamiltonian is a collective operator sigma z1 plus, sorry, this should have been 2, plus sigma z2 coupled to some Balf operator. But the point is that there's the same Balf operator coupling to the two sigma Pauli matrices. Okay, it is not sigma z1 b1 plus sigma z2 b2. No, they're coupled collectively. Now this Hamiltonian is trivial to write down in diagonal lines. It's already diagonal in the computational basis of up-down states, the 0-1 states. And what you see is that there is a degenerate subspace. Remember the theorem from the previous slide. It was talking about how the dimension of the DFS is the degeneracy of the one-dimensional irreducible representations. All the irreducible representations here are one-dimensional, and there is one irreducible representation which is two-dimensional. It has degeneracy 2. So that suggests that we should encode, just like in quantum Rickardt encodes, and now we're doing decoherence subspace encoding, we should encode our qubit into these two states. The up-down, we'll call it 0-1, and the 1-0 state. Okay? So these two yellow states here became the blue states down there. That's our logical qubit. It's protected. Why? Because the environment acts in an identical manner on those two qubits. Here, if you don't see it, then let me do it in excruciating detail. Here is the transformation once again with that same phase, hence collective dephasing. Here's what happens to our two qubits. The state 0-0 is unchanged. The state 0-1 acquires a phase e to the I theta. The state 1-0 also acquires a phase e to the I theta. And the state 1-1 acquires a phase e to the 2 I theta. Now, a global phase, as Mohammed mentioned in his first talk today, a global phase is irrelevant. Okay, so if we call these two states our logical 0 and logical 1, this is like the odd parity subspace, then any linear superposition of these two states is going to be decoherence free. Because all it gets from the environment is a global phase. So it will not decohere. There will, however, be decoherence between this state, the 0-0 state, and this state, because they get a relative phase. Okay, and that phase is random. Depends on how long the environment is coupling to a qubit. So there will be decoherence between the 0-0 and the 0-1 state, but not between the 0-1 and the 1-0 state. And that's why we should stick our quantum information in there. And what we get is a two-dimensional protected subspace, a two-dimensional decoherence-free subspace. Okay, so this is really not much more complicated than the example of the two coins, except that now we're working with phases as opposed to flipping. Oh yeah. Any idea? Are these two states also a DFS? Is the state 0, 0 a DFS? Yes or no? Well, it's kind of a trivial DFS. It's just a single state, okay? But it is a one-dimensional irreducible representation. But it has degeneracy 1, so you wouldn't want to store any information in it. It's like having only one side of a coin to work with. Not very useful. So here's where you want to store your information. That's the actual full cube. Okay, so now on to noiseless subsystems. So remember, I talked about the subsystems. We had this issue with how the subspace A got decomposed into n tensor G. All right, so let's see how that shows up in this context of symmetry and irreducible representation. As was realized in this beautiful paper by Flom and Viola a decade ago, in fact, this condition about one-dimensional irreducible representations is not needed. The 1D is not needed. Okay. So the mathematical formalism behind it is a little heavy, but it's not too bad. Here again is the model of decoherence. We have a system bound interaction. And just like before, let's consider the algebra of polynomials in the system operators, their Hermitian conjugates, and the identity operators. Let's consider this algebra. And let's assume that we have n qubits. Okay, so if we have n qubits, then we have a Hilbert space which is C2 to the n. It's a 2 to the n Hilbert space. Now, if you think about what the action of the algebra is on this space, Hilbert space of n qubits, this generates a representation of the algebra. And this representation breaks up into irreducible representations. And how does it do that? Well, there's a general theorem which says that this algebra is isomorphic to a tensor sum over tensor products. The sum is over labels that are called irreducible representations, just like an angular momentum theorem. And the amazing thing is that this tensor sum is composed of tensor products where each tensor product contains an identity operator times some matrix. So the identity here is what's going to be key for us. This is somehow the whole secret to being able to store information. Because this algebra is what causes the errors. And if the errors act as identity, then they're not errors. All right. So what is the dimension of these identity operators? It's exactly the multiplicity of the J irreducible representation, or the degeneracy. Multiplicity and degeneracy means the same thing. Okay. And what's the dimension of these matrices here? What these matrices are irrelevant. The only thing that we need to know about them is what's their dimension. Their dimension is whatever the dimension is, dj. Okay, so once you have the structure, the Hilbert space, the system Hilbert space, decomposes accordingly. It decomposes into a tensor sum of tensor products. Each tensor product has a piece that is nj dimensional, the multiplicity or the degeneracy, times dj dimensional. Okay? Each one of these j's, each one of these irreducible representation labels a noiseless subsystem code. Okay, so where we store information is in one of the elements of this tensor sum. Let's pick out one of them. Let's say the first of the j. That j is associated with a subsystem that is nj dimensional. Nj, once again, is the degeneracy, or the multiplicity of the j representation. And this is where we're going to put our information. That's a noiseless subsystem. What's a DFS? A DFS is the somewhat trivial case where the corresponding dimension of the irreducible representation is just 1. Okay? When the dimension is 1, then when you do the trace out piece, remember tracing out G, n tensor G, you're tracing out G. Well, there's nothing to trace out when the dimension is 1. That's how you get a DFS. Okay, what is the interesting case? When do we actually gain from this kind of structure? We gain when the multiplicity, the degeneracy, is greater than 1. Okay, so I gave you an example with the collective dephasing where the degeneracy was greater than 1. We had a degeneracy of 2. When does that happen? It happens if there's some symmetry, because degeneracy is connected to symmetry. That's Noether's theorem. All right, so this is the general structure for Noiseless subsystems, and this is actually, although I know that it looks very abstract, it is actually a constructive recipe for finding Noiseless subsystems. What do you need to do constructively? Well, somebody hands you a system bath Hamiltonian, you plug it into Mathematica and ask it to find the irreducible representations, and it will spit them out. And then you can find the one that has the largest degeneracy, and that's where you're going to put your quantum information. Okay, so here's an example. I talked about collective dephasing. Let's make the model more interesting. Let's say that we don't just have collective dephasing, we have collective decoherence. So collective decoherence is errors in all directions, but they're all a long wavelength. Okay, so we have a long wavelength magnetic field along Z, along X, and along Y. Here again are 2 qubits. And this could be, for example, the situation at low temperature when decoherence is due to phone lines. Okay, so formally, the error model is described by a system bath Hamiltonian that has collective error operators acting on the system. Once again, there's no B alpha J, there's just a single B alpha. Alpha is X, Y, or Z, depends on which direction the error is. And each B alpha is coupled to a collective spin operator, a total spin operator. Okay. So that's at the level of Hamiltonians. You can also think of it at the level of CP maps, if you prefer. Then the state is transformed into a collective rotation with some probability. Collective rotation along X, probability P1, etc. Okay? This is an entirely equivalent way of looking at the problem. One is at the level of Hamiltonians, the other one is at the level of CP maps. Collective rotations versus collective generators of rotations. With Hamiltonians. All right, so now how do we find the DFSs in the Noiseless subsystems? We have to do the analysis in terms of the irreducible representation of the Lie algebra SU2, because that's what we're dealing with here. Okay, this is S alpha, SX, SY, SZ together generate SU2 on n qubits. So we're trying to decompose SU2 on n qubits into its irreducible representation. And fortunately, there's a very nice graphical way of seeing how that's done. It's called the Bertelli diagram. And the Bertelli diagram goes like this. So over here, I'm plotting the total state, which I'm calling J. And over here, I'm plotting the number of qubits. All right, so let's say that we have nothing. Okay, so 0 qubits have 0 state. Now let's say I have 1 qubit. It's a spin 1/2 particle, so I'm going to put a point here. Let's have 2 qubits. If I have 2 qubits, they can either form a spin 0 state or a spin 1 state. If I have 3 qubits, they can form a spin 1/2 state or a spin 3/2 state, etc., etc. Okay, so that's the beginning of the Bertelli diagram. Now, what is this formula? How is it represented? The Hilbert space decomposition. What does it actually mean in this case? So here, I'm assuming that n, sorry, this is capital N, it should have been lowercase n. N, whether capital or lowercase, is the number of qubits. So let's fix an n. Let's say n is 2. Okay, so when n is 2, I have one way, this path, up, down, to get to spin 0. Remember that when I talked about the theorem for decoherence for subspaces, I was talking about the one-dimensional irreducible representations. This is the only one-dimensional irreducible representation for 2 spins. There's also a 3-dimensional irreducible representation up here. But this one is the one that will give me a decoherence-free qubit, and this this is the state. Okay. Now, for 3 physical qubits, there are 2 ways to get to this point. Now it's interesting. Now we have a degeneracy. I can go up, down, up, or I can go up, up, down. Now there is a degeneracy. The degeneracy is reflected in the number of paths leading to a given point in the Bartelli diagram. So here are these 2 paths. I plotted them. And I also wrote down what the states are. To get the actual states, you can't just read them off easily from the Bartelli diagram. You actually have to calculate Clebsch-Gordan coefficients. So when you do that, you find that these are the 2 states corresponding to these 2 paths, which lead to the same point on the Bartelli diagram. Again, path is like degeneracy. Paths leading to the same point tells you the degeneracy of an irreducible representation. Here we have a irreducible representation that is 2½ plus 1, so 2-dimensional, and it's twice degenerate. Okay, so this actually gives you a qubit. This just gives you a single state. I think I misspoke earlier. I said this is a qubit. It's not. It's just a single state. Okay, it's a decoherence-free state. Here we have an actual qubit. And decoherence-free actually a noiseless subsystem qubit because it's not associated with a singlet. Singlets are the states that live on the horizontal axis. Here's another one. 2 paths, up, down, and up, down, down. These 2 also give you a decoherence-free qubit. This is really a DFS. It's associated with the singlet state. Again, the singlets live on the horizontal axis. And that's what the actual states are. So if you're looking for subject to collective decoherence, if you're looking for the smallest possible protected qubit, you'll find it right here. Small in the sense that it uses up the least number of physical qubits. Only 3 physical qubits are used in order to get to this point. Or you can use 4 and get here, or, okay, you see the numbers, right? So 2 is a qubit, 4 would be 2 protected qubits, and 5 is well, 5 whatever you call that. Okay, so in this way, this diagram actually decomposes the Hilbert space precisely according to this formula. You fix n. Let's say we fix n at 4 now. The number of physical qubits is 4. What is this formula saying? It's saying j equals 0. We have a 2-dimensional, a twice degenerate irreducible representation, and a 3-wise degenerate irreducible representation, and another one here that's only 1. Okay, and this way, for each value of n, you're decomposing the Hilbert space, and you can read off all the decoherence subspaces and Noiseless subsystems. Okay, now, how does this thing scale? What is the rate of these codes? In Daniel Gottesman's lecture, he probably talked about the rate of codes. And the rate is some kind of measure of their performance. It tells you how many physical qubits in, gives you how many physical qubits out. And of course, you want to get as many physical qubits, logical qubits out. You want to get as many logical qubits out per physical qubits in as possible. So these codes are actually sort of amazing in that regard. This is the general formula for any point along the Bartelli diagram. And in particular, if you're looking for the singlets, which is j equals 0, the number of encoded qubits to physical qubits is the log base 2 of this expression divided by the number of physical qubits. And as n gets large, it goes to 1 minus a logarithmic correction. Okay, so asymptotically, the number of decoherence-free qubits actually fills up the entire Hilbert space. Okay, this is a code that has an asymptotic rate of 1. Of course, if life were only that good, right, I mean, there's a small assumption here, which is that our errors act in a symmetric way. And, well, maybe they don't. All right. Okay, so far I talked about storage, but what about computation? So, in order to prevent decoherence, we have to make sure that the computation doesn't exit the Hilbert state, the protected subspace, the DFS or the Noiseless subsystem. So what are the compatible logical operations? What is it that we're allowed to do? This is like the question about normalizers in error correcting codes. You have a state logic code, normalizer tells you what are the allowed operations on that code. So we can ask a similar question here, which in fact is, includes the normalizer, stabilizer thing as a special case. And the answer comes from that formula, the ERAP formula for the error algebra. So here it is again. This is the associative algebra of the errors. And here is the decomposition of the Hilbert space. And here is the code subsystem where we're going to store information. We're storing information in the degeneracy of the Jth irreducible representation. Now, the allowed operations, the answer to what are the allowed operations comes from this observation. There are operators, the Hamilton, which commute with the error algebra. A prime, all those operators which have this dual structure where there's a matrix, tensor identity, which is precisely the opposite of this structure. Okay, the dual structure. Obviously, any operator that can be written in this form commutes with the errors. If an operator commutes with the errors, that means that it doesn't couple to the errors. Okay, so the errors are not going to mess up that operation. So that operation, M prime, acts precisely in the right place. It acts on our code subsystem, and it acts in a way which will not be messed up by the errors, because it commutes with the errors. So those are the allowed logical operations. And it turns out that for an important example, namely for collective decoherence, we can identify specifically what these allowed logical operations are. It turns out they are precisely the so-called Heisenberg interactions. Okay, so Heisenberg interaction is an interaction of this form. It's a pairwise interaction between qubits. It is symmetric between x, y, and z. It couples pairs of qubits. And it also turns out that it's possible to perform universal computation in the sense of the circuit model, not in the sense of adiabatic computation. In the sense of the circuit model, it's possible to universally compute using just the Heisenberg interaction by turning on and off these coupling parameters Jij over these Noiseless subsystems type codes that I've described to you. So Heisenberg interaction is universal all by itself over these codes, over Noiseless subsystem codes and decoherence subspace codes. Okay, so here it is in a little bit more detail. Here's the Heisenberg exchange interaction again. And let's write the exchange operators, x, I, j, etc. Let's just call them Eij. And it's called Heisenberg exchange because you can show that this operator Eij is actually like a swap. Okay, it acts just like a swap. So you can ask, well, what are the operations which implement computation using exchange operations? So if you look at the 4-qubit DFS, remember the 4-qubit DFS, it was this code. If you remember my conventions, okay, this is what I call logical 0, and this is logical 1. Okay, over this 4-qubit DFS, you can identify explicitly what the exchange operations are that implement logical x and logical z. Logical x is an operator which interchanges logical 0 and logical 1. Logical z is one that puts a relative phase between logical 0 and logical 1. Okay, so it's very easy to check that indeed the exchange of, let's say, qubits 1 and 2 puts a relative phase between them. I think we can check that right now. So exchange 1 and 2 means flip 0 and 1, flip 1 and 0 right here. So that's going to pull out a minus sign. Okay, so it puts a minus sign on logical 0, but it does nothing to logical 1 because you see the first two qubits are always the same here. Here and here, they come in a way that cancels the operation. So we get a minus sign on the 0, and we get a plus sign on the 1, and therefore negative exchange 1, 2 implements the logical z operation. Okay? And you can check that logical x, the thing that interchanges 0, logical 0, and logical 1, is this sum of exchange operators. So once we have logical z and logical x as generators, we can exponentiate them. These are terms in the Hamiltonian, okay? So this is where it connects to the stuff Mama was talking about. I'm working at the level of Hamiltonians now. These are not gates. This is not an x gate or a z gate. This is an x in the Hamiltonian. It's a sum of exchange operators. It's a piece in the Hamiltonian. So I can imagine turning it on and off for the right amount of time to turn on e to the I theta x bar, e to the I theta z bar. And now I can generate arbitrary single encoded DFS gates. Okay? So the single encoded DFS gates are easy. They're generated by these operators. The control knot, the encoded control knot, is very hard. It involves 42 elementary steps. By elementary step, I mean operations generated by turning on and off some sequence of exchange operations. And you can find the details in Dave Bacon's PhD thesis, where this was worked out. So this actually has implications beyond protecting information. I guess, let's see, 5 or more years ago, there was some excitement in the quantum dots community because it was realized that using exchange operations alone, they could implement universal quantum computation. It comes straight out of these results. And in the quantum dots community at the time, it was thought to be very hard to implement single physical qubit operations. They wanted to do everything with exchange because exchange operations are very fast in quantum dots and also relatively easy to generate. So for a while there was some excitement because people thought that this would be a good way to actually perform universal computation in quantum dots using these codes and then using just exchange operations to do everything. I think by now other methods have been discovered which actually go back to just addressing single physical qubits optically and electrically, which may obviate the need for this method. But who knows? It might come back. All right, so I want to talk a little bit about the experiments that have been done to confirm the existence of DFSs and or the subsystems. So the very first experiment was performed by Paul Kriot and his group. And it was an optics experiment using parametric down conversion. They generated pairs of entangled photons. So here is the scheme of the experiment. This is a 2-qubit or 2-photon experiment. And the goal is to generate the singlet state, this state right here. Okay. And to show that it is robust against collective decoherence, or collective decoherence. Okay, so here is the photon source. You get 2 photons coming out of this parametric down conversion process. They go through half-wave plates, and they go through some quartz plates, which generates the decoherence. And in this experiment, which is somewhat artificial, these quartz plates were manufactured to be as identical as possible, so that the decoherence would be collective, identical on the 2 photons. Okay, and then there is some tomography set up here, which you need in order to get the results. And what they saw is summarized in this graph. I hope everybody's a little bit familiar with reading these kind of tomography plots. Basically, what you're seeing here are the 4 polarization states, horizontal and vertical polarization. And the 4 bars up here represent the singlet state. If you think about the density matrix in the horizontal vertical basis, the singlet state, the one that is 0, 1, minus 1, 0, over root 2, this state is these 4 vertical bars. The other 3 are the other 3 states that belong to the triplet. And as you can see, their amplitude is diminished. They have decohered. Okay, whereas the singlet state has been, it's a little hard to tell from this experiment, it was the first experiment, but you can sort of see that the singlet state went through and didn't get damaged. This is the tomography of the singlet state at the output. It got preserved with some high fidelity. The tomography of the 3 singlet state shows that they got damaged by decoherence. Okay, so this experiment demonstrated that the singlet state is indeed robust to collective decoherence. Okay, this was in 2000. A year later was the first experiment on noiseless subsystems. It was the 3-qubit noiseless subsystem. Remember the Bertelli diagram with the 2 paths leading to the same point with 3 physical qubits. That's precisely what was tested here using nuclear magnetic resonance on this alanine molecule. So the molecule has 3 carbon atoms which are isotopically labeled and can be distinguished. And it's possible to control the interactions between them, these J's here. So the experiment prepared the noiseless subsystem qubit over 3 physical qubits, the nuclear spin 1/2 of each of these carbon atoms. And the hydrogens in this molecule provide the environment. The hydrogens are spin 1/2, so they are like a spin bath coupled to these carbons. And what they saw, they measured fidelity, entanglement fidelity, as a function of noise strength. So noise strength here is, how exactly they did it, I don't recall. But noise strength is in a sense, the rate at which you're doing the flipping. Like the rate at which I was flipping the 2 coins in the beginning of the talk. And what you see is remarkable. You see that no matter how strong the noise, these curves here, which represent the entanglement fidelity of the noiseless qubit, are totally flat. Okay, and this confirms this prediction that when you have symmetry protecting your information, it doesn't matter how strong the system valve coupling is. The information is protected, independent of strength. Whereas if you just look at a raw qubit, it decays. Its fidelity decays as a function of the noise. Now you may be wondering why these curves are so much lower, and that would be a good question. And the answer is that it takes a while to prepare the noiseless qubit. Okay, so you lose a lot of entanglement fidelity just through the preparation step. But once you have it prepared, then it's robust. Okay, and they took it out to the regime where you can see that the fidelity actually is better for the noiseless qubit than it is for the unprotected. Okay, so this was 2001. Then 2004, there was an experiment again in quantum optics, not involving the 4-qubit DFS, once again this one. And using 2 pairs of entangled photons. And in this case, you see the U's here represent collective rotation. So every photon underwent the same rotation operation, random rotation U. And once again, tomography results, what they're showing here is the input state and the output state. And they decided to prepare this particular superposition of the logical 0 and the logical 1, square root 3, logical 0 minus logical 1. Okay, and that's what this state is, and you see that the input is essentially identical to the output. Okay, so this collective decoherence channel was unable to damage this protected qubit. Okay, so once again, a nice demonstration of how it works. Okay, well, the next question is, all right, so we have this nice symmetry. We're assuming that there's a symmetry, but what if it's broken? What if the symmetry is imperfect? So if the symmetry is imperfect, well, it could be either weakly imperfect or very imperfect. So let's imagine this perturbative regime where it's weakly imperfect. We just introduce perturbation onto the system math Hamiltonian, and that has some strength epsilon. But we're assuming that the system math Hamiltonian has a symmetry that gives rise to a DFS or another subsystem. And then this extra piece, delta H, doesn't have any symmetry. Okay, and let's characterize the strength of this perturbation by epsilon. And then what you can show is that the DFS or the NS, the noisy subsystem, is going to be stable to first order. So you can show that automatically you have protection to first order in epsilon, and the fidelity is perturbed only to second order in this parameter epsilon under symmetry gradient. Okay, so this is a little bit like the result for error correcting codes, except that with error correcting codes, because we have this additional active correction step, we can perfectly restore the fidelity. With the DFS, it only lives for a short time, depending on the value of epsilon. And in fact, there was an experiment which tested this, once again from Paul Kriot's group. So they looked at the 2-qubit DFS. So this should remind you of the first experiment from the Kriot group, except that there's some additional components here. Without getting into the details of the experiment, what they checked was the robustness to a perturbation epsilon. So there's here's the singlet state. Here are the 3 triplet states. I don't know how easy it is to see it from a distance, but if you look carefully, you will see that the singlet state, as a function of the perturbation, the fidelity drops off quadratically. Okay, so here the fidelity is perfect. That's when the 2 qubits, the 2 physical qubits, are rotated by the same amount at random times. So they're both rotated by 15 degrees at random times. And then over here is when one of them is rotated by 15 degrees, but the other one is rotated by slightly less, and you see how the fidelity drops off quadratically. Okay, so that's this first order stability result. That's to rotation errors, and then to strength errors, same story. Singlet state, over here, 140 waves is the benchmark, and then if you apply a thicker plate to the second qubit or a thinner plate to the second qubit, you see that the fidelity only drops off quadratically. Okay, so this demonstrates the robustness of a DFS to first order. Now, what about strong symmetry breaking? So we had perfect symmetry, we had weak symmetry breaking, strong symmetry breaking. This is an experiment which was not really meant to demonstrate strong symmetry breaking. At least you won't find that in the article, but I'm interpreting it in this way. This is a demonstration of a DFS from Dave Wineland's group using trapped ions. Okay, so 2 beryllium ions, and the physical qubits here are hyperfine states of each ion, and the sources of decoherence are 2, primarily. One is fluctuating long wavelength ambient magnetic fields. So if you know how an ion trap experiment works, you have these Paul traps that have these lengthy electrodes, lengthy relative to the distance between the ions, and provide electromagnetic confinement. And these electrodes had, at least used to back in those days, I think the situation has improved somewhat, they used to have these kind of random magnetic fields, long wavelength, that would just occur spontaneously and nobody really understood why. And they were causing decoherence. But the key is long wavelength relative to the distance between the ions. So that's one source of decoherence. The other one is the heating of the ion center of mass motion. Now, source number 1 obviously has a symmetry, okay? It has this perturbation symmetry, long wavelength. Source number 2, the heating of the ion center of mass motion, has no symmetry at all. So here we have a case where we have something that's going to allow a DFS, something that's going to break the DFS. And that's actually what is seen in the experiment. Here you have some measure of coherence as a function of time. And you see that if you don't do the DFS encoding, the coherence decays exponentially very fast. And if you do the DFS encoding, this DFS that we saw earlier, the coherence lives a little longer, about 5 times longer in this experiment, which means that you protect it against source number 1, but it still falls out exponentially. And that's because you haven't done anything to protect against source number 2. Okay, so this is a case of strong symmetry breaking, which we have to deal with. And indeed, that's what I'm going to do after the break. Any questions?
I want to make sure if I understand the DFS and noiseless subspace.
Subsystem. Yes.
Subsystem. So we have many qubits, physical qubits, and the noise is kind of total SC and total SC squared. And if you have enough qubits, you can always have irreducible representations with total J equals 0. So you pick two of them and call one of them the logical 0 state and the other logical 1 state. And that's the DFS.
Well, if you have a lot of physical qubits, you can do more than just a single logical 0, logical 1. You can create lots of logical qubits.
Right.
Okay? In fact, for the case that you described where it's collective dephasing, just the D component, you just need 2 physical qubits to create a single logical qubit. And the combinatorics is actually easy. It's very easy. The combinatorics is just the binomial formula, nothing else.
Right.
Yeah.
That part I understand.
Okay.
So for the noiseless subsystem, is it because if you have enough qubits, physical qubits, then you can always have 2 irreducible representations with the same J. Then you pick the corresponding JZ part as 0 and 1, so they have relatively no noise.
I hesitate to say yes. The way to think about it is, for a given value of j, the total j, find the degeneracy.
Yeah.
The degeneracy is going to tell you the dimension of the noiseless subsystem.
Right.
Or of the decoherence in subspaces, it happens to be dj equals 1.
Yes.
Okay?
So the noiseless subsystem, you can only pick the ones with JZ the same value, is that right? You have to pick the ones with the same JZ.
Yes.
Okay.
Yes, that's right. Okay. All right, let's take a break.